What's up, guys? Good morning to you, and today we are going to go through the law of gravitation worksheet. Okay, so we took the notes on the universal law of gravity yesterday, and here's some practice problems to kind of go over them. What I'm going to do today is just kind of go through each and every one of them so that you have an understanding of if you're doing them right. So what I would encourage you to do is try to go through as many of these as possible on your own real quick, and then check your work here. Me. Okay, so I'm going to go ahead and get started now. So if you wish to pause and come back later, that would be encouraged. Let's go ahead and start with number one here. It says, what is the equation for the gravitational force of attraction between two objects? Okay, the equation for gravity, it says it right here. So there's our formula. Our force is equal to G times M1 times M2. We're going to divide those by the r squared, okay, where r is the distance between the two objects, the distance between their centers. Okay, what is the value for g? Well, the value for g, it shows right here. That's g. Okay, so if you just want to rewrite that number, 6.67 times 10 to the power of negative 11, and that's the value. Okay. All right. Next is, what type of mathematical relationship is the law of universal gravitation? Well, since there is a fraction here, it is going to be called an inverse relation. Okay. In the law of universal gravitation, distance is measured from where? We have two masses, right? We have two masses. Where do we measure their distances from? Because they're touching, aren't they? You see these two circles? If they're touching, well, are they 0 meters apart? No, right? We're measuring apart from their centers. So it's measured from their centers of mass. Okay, measured from the centers of mass. All right. Now we're going to explain what happens to the gravitational force of attraction between two objects if they're moving together. So what happens if you get closer to something? Does the gravity increase or does the gravity decrease? If we look at it, this number would be getting smaller. Smaller number on the bottom means you're going to have a larger number in the end. Okay? It increases. Okay? Next one, what happens to the gravitational force between two objects if the mass of one of them is doubled? Okay, so if the mass of one of them is doubled, the mass is on top, you're going to have 2 times one of the masses on top, so the end result will be multiplied by 2. Okay, the gravitational force will be doubled. If both of them are doubled, if we have both of them on top doubled, so that's 2 times 2 times the masses, it's quadrupled, right? I don't know if I spelled that right. Multiplied by 4. Okay, doubled is times 2. What happens if the distance between them is doubled? If the distance, which is r, if the distance between them is doubled, then we're going to have 2 here, and then we're going to square that. If we double the distance, we're going to square that, so that's 2 times, or 2 squared, which is 4. And notice it's on the bottom. It will be divided by 4. Okay, if the distance between them is doubled, our end result will be divided by 4. Notice these ones are increased by a factor of 2, increased by a factor of 4. This one will be decreased by a factor of 4. Okay, distance doubled means less gravitational force. The distance between them is cut in half. Okay, so if we have this one, I'll have to look at this one on a thing. So we have M1, M2, nothing's happening there. On the bottom, we have our distance is cut in half. So we have 1/2, and we're going to square that, which is equal to 1 over 1/4. Well, 1 divided by 1/4. How many times does a 1/4 go into 1? That's 4. So quadruple it. It's 4. Let's see if that makes sense. If we cut the distance in half, we're getting the two objects closer. If two objects are closer, do we think the gravity is going to be more, or do we think it's going to be less? More or less if there's less distance? Distance is cut in half. Definitely it is going to be more because we're getting two objects closer. As they get closer, the gravitational pull becomes stronger. Think of it like this. You have two magnets, right? You have two magnets, you set them on the ground. As those two magnets inch closer, the gravity between them starts to get stronger. You can start to see them react to each other. Eventually, if you get them close enough, what happens? Boom, right? They accelerate towards one another until they are touching and holding each other. So that's the same concept as gravity. Okay, magnetation or magnetization or magnets and gravity work very, very similar. Okay, let's go ahead and look at the backside now. It says, why do you think you weigh slightly less when you're on a plane that is flying in the high air? Okay, well, if you are in the air flying in a plane, what do you know about the equation? What's going to change? Okay, so let's look at what's going to change. Is it going to be your mass? No, your mass is not changing. G is always constant. How about the distance between you and the center of the Earth? Well, that is going to be changed, right? Because you're up here somewhere, you're flying up here versus on the ground. If you're on the ground, that distance is smaller. If you're flying, the distance is slightly bigger. Okay, so you weigh slightly less. You weigh slightly less because the distance which is r, increases. Okay, if the distance, which is r, increases, that means that your gravitational force decreases. Calculate the force of attraction between two 55-kilogram people standing 0.25 meters apart. All right, cool. So we've got the formula F equals G M1 M2 divided by R squared. I encourage you to pause it and try this one. So G is 6.67 times mass 1. Sorry, I'm gonna do a little bit of something that's slightly different than the book does. Instead of putting the times 10 to the negative 11 right here, I'm going to put it at the end. Times 10 to the negative 11. 52, 55 kilogram people. So we have mass 1 is 55. And what's our mass 2? Well, both of them weigh the same. They're both 55. Okay, and they're standing 0.25 meters apart. So 0.25. Remember, we're going to square that number on the bottom. Okay. Now I'm going to get my calculator. If I can find it. Oh, no. All right, so I found my calculator. We've got, to type that in, I'm going to put 6.67 times, on top we have 55, and another 55, And on the bottom, we have 0.25 squared. Notice how I put that in parentheses because I want that to happen. Okay, and I'm going to ignore the 10 to the negative 11. That just tells me where the decimal goes. So I'm going to hit enter here, and I write that number down. Okay, so I have 3.22, 828, and we still have times 10 to the negative 11. I know that there's a way to type it into the calculator, but I am not a professional calculator typer. So what I would do is I would convert this. So this is, if I rewrote this in scientific notation, that's 3.22828 times, well, this one is 1, 2, 3, 4, 5 times 10 to the 5. And we still have the times 10 to the negative 11. And that will give us our answer. Oh man, it's going to be tough to squeeze it in. 3.22828 times 10. Remember, if you're multiplying the same bases, we have 10 to the 5th and 10 to the negative 11th. You add the exponents. 5 minus 11 is negative 6. And this would be our answer right here. Hopefully that made a little bit of sense. For those of you who did not make sense, all I did is I rewrote this number right here into scientific notation, which is right here. If you remember our scientific notation unit, that number could be written as 3.22828, right? Because you always put the decimal after the first non-zero. There it is. And then you find out how many decimals that it would be moved from right after this 3. So I went 2 to the right, 5 to the right, 1. I went from here once, twice, 3, 4, 5 times. That's where I got 10 to the 5th from. I added the exponents. 5 minus 11 is negative 6. All right. There's my answer. Number 9. The distance between the Earth and the Moon is that the Earth's mass is there and the mass of the Moon is there. What is the force between the Earth and the Moon? Okay, so once again, let's start off by writing the equation. And again, I encourage you all to maybe pause the video and attempt it on your own. I wish there was a way to zoom in. I don't know if there is. I am trying to zoom in the camera right now. I don't think it's possible. Oh well. Okay, so g m1 m2 over r squared is equal to, so let's see what we've got here. First off, g, we'll put it as 6.67, right? And that's going to multiply all of our stuff here. I'm going to give myself plenty of room there. And remember that I'm going to put the 10 to the negative 11 out here because I'm not a professional calculator typer. I'm sure that we could type it into the calculator, I just don't know how. Okay, after that, I'm going to put the 3.84 on top. 3.84, that's my mass 1. The 10 to the 8th, let's throw it out here next to the other 10. Okay. Oh, that's my bad. I'm sorry, guys. Shucks. Okay. That said that the distance is that. I put that as one of our masses, which it is not. That's my bad. Okay, so that's a distance. So that 3.84 is going to go on the bottom. And if I put that on the bottom, that means the 10 to the 8th is going to also be on the bottom. Okay, I'm sorry about that, guys. That's my bad. Okay, and now it says the Earth's mass is that. So I'm going to write that one on top, 5.9742. And the 10 to the 24th will go out here. Okay, that's right. That's my mass 1. And mass 2 is there. and 10 to the 22 right here. See, that's how many decimal places. It's quite a bit. Okay, that's why I don't want to write it with the zeros. What is the force? All right, so now here's what I will do. Okay, I'll type that into the calculator. First off, I actually want to see what's going to happen down here. Remember that this number right here will be squared. Now, I don't want to confuse anybody too badly, but I'm gonna rewrite this whole thing just to make it a little bit easier to see. So that's 6.67, and then on top 5.9742 times 7.36. All that will be divided by this, but I want to simplify this first. So first off, I know that 3.84 is going to get squared. And so is this 10 to the 8th. Now, there's an exponents rule. If you recall, if I have 10 to the 8th and that gets squared, what am I going to do with these two numbers? I'm going to do something. Am I going to add them? No, I'm only going to add them if they're next to each other, kind of like this 5 and the negative 11. That became negative 6. If there's a 10 to the 8th squared, that means I'm going to multiply those two. So that's 10 to the power of 16, and it's on the bottom. Okay, it's on the bottom. So I'm just going to be writing these. So if I have 10 to the 16th on the bottom, then I can rewrite that as 10 to the negative 16, because it's on the bottom of a fraction, so it's negative 16. So now I have something that looks a lot simpler to multiply in my calculator, and then I have all this mess. Okay, I can clean that up later. So we've got 6.67 times 5.9742 times 7.36 divided by, I'm going to put parentheses, 3.84 squared, close parentheses. And I get that. Okay, I'll write it. Oh, we'll go to like, I don't know, 4 decimals. So I'm going to put 19.8893. And that 3 will round up to a 4 because the 6. Okay? All right. Now, once again, I'm going to move this. I'm going to rewrite this number, though, in scientific notation. So that's going to be 1.9. 1.9889. And I'll leave it like that. I'll let the 3 round the 9 down to the 9. Okay? That would be times 10 to the exponent of, well, I moved it once to the right. So exponent will be 1. Now I'm going to rewrite all this stuff. So times 10 negative 11, 10 24, 10 22. We're almost done with this one. 10 to the negative 16. Okay? If I do that, I get 1 point, I just rewrite that. 1.9. Almost done, I promise. 889 times 10. Now we get to add all these up. That's fine. Okay, so we have 1 minus 11, that's negative 10, plus 24, that'd be 14, plus 22, that'd be 36, minus 16, that'd be 20. So there's our answer. All right, I know that was confusing. And I also know that if you have an advanced calculator, you can do it there a lot easier than I can do it on my calculator, which has limits. So, I mean, I can try to do it. Let's see if I can actually figure this out. 0.67. I'm going to go from the very beginning to see if we can avoid all of this stuff. I'm not sure if I can. Okay, times 5.9742 times 7.36. We're going to divide that by the bottom. I'm going to put double parentheses 3.84 times 10 caret 8. Close that. We're going to square that. Close that. Times 10 to the negative 11. 10 caret negative 11. I want to put that in parentheses because to me that makes it more clean. I'm going to put times next one. Next one was 10 to the 24. 24. Close. Times 10. The last one is 22. Fingers crossed. Let's go. Oh, look at that. If you actually are able to type it in, 1.9889, and then you see where it says the 20 right there? That just means times 10 to the power of 20. Each 20 decimals off. So everything we did was right. If you know how to type this into the calculator, and you're a calculator wizard, you can do it. I guess I'm a calculator wizard. Didn't know it. Okay, so all the stuff on top, and then on there's 7.36. I divided the 3.84 times 10 to the 8th, and then I squared that, and then I went times 10 to the that, negative 11, 10 to the 24th, right there, and 10 to the 22, right there. So there is a way, it is definitely possible to do it in calculator if all of this, which is possibly true for most of you, probably true for most of you, if this is a lot more difficult, then I would encourage you to become a calculator wizard and do it like that. It's a long string of numbers, and it pretty much has to be all typed in at the same time. Okay, so running through that again. Yep. Anyways, let's go on to the next one, guys. So, circular motion, angular speed describes how fast something rotates, degrees per minute, and rotations per minute, RPM. Those are the two common units of angular speed. So here it is, angular speed, rotations or degrees over time, right? Remember that speed is kind of like distance over time. Well, instead of distance, we're just using rotations. The radius is the distance from the axis of rotation to any point on the outside of the circle, which many of you know from math. Okay, here's our circumference formula. R, of course, is the radius of the circle. Okay. Circumference describes the distance traveled during one revolution. Circumference, of course, is the distance all the way around the circle. That's circumference. Okay. That's the distance traveled during one revolution. Okay, linear speed, that describes how fast the revolving object travels. Linear speed is often given in meters per second. So here's our linear speed. 2 pi r, which is circumference, divided by time, where r is the radius and t is the time for one revolution. So let's answer the following. We know that rolling is a combination of linear and rotational motion. So when a wheel makes one full rotation, it moves forward a distance which is equal to, of course, the wheel's circumference. So larger circumference means you're going to go farther with your wheel in one rotation, right? If I have a big giant wheel, it's going to go a lot further in one rotation than a little wheel, such as this wheel on this car. Okay? This wheel on this car is not going to go very far if it does one full rotation. So let's see, it goes right there, comes right back around, right there, boom. Okay, smaller wheel. Now if we have a larger wheel, it's going to come all the way across the paper, be way out there off screen. Okay, so And we have four little parts here. A child's first bicycle has 12-inch tires. These tires have a 6-inch radius. Okay, 12 is the diameter. How far does the bicycle move forward each time the wheel makes one complete rotation? So we're going to give our answer in meters. Well, how do we find that? Remember, we're just finding circumference. Circumference is 2 pi r, where pi is that 3.14 number. Okay, so 2 times pi times r. Pi is not a variable, it's a number, and r is our radius. So what's our radius here? It says 6 inches. Ooh, we need to give our answer in meters though. So instead of inches, it wants it in meters. So here's our conversion factor. 1 inch equals 0.022 meters. So here's how we're going to do that. So 2 pi times 6, but that's 6 inches. So I know that I want to get rid of inches and I want to convert it to meters, right? So here's our conversion factor. If I want to get rid of inches, is inches going to go on top or bottom? Well, inches is on top here, so we want it to cancel out. So inches over one bottom. So 1 inch on bottom. 0.22 meters will go on top, and we'll have our answer. So that's 2 in our calculator times pi. Where's the pi button? I'm sure it's here. I'm sure that you guys are all screaming at me where it's at, but I do not see it. Where's that pi button? Nope. 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 There it is. Oh man, I found it. I'm sorry, guys. I was not able to find that. So there it is. So 2 pi and then times r, which is 6, but it's not 6 because we need to convert it. So we put 0.24 or 0.22 over 1. Okay, there it is. We'll have our answer 8.29. 8.29 what? Well, we're measuring the distance around the circle, so what's our unit? Converted to meters, so distance is measured in meters. All right. A woman's 10-speed bicycle has 27 inches tires. There's our radius. How far does this bicycle move forward each time the wheel makes one rotation? Give our answer in meters. So once again, 2 pi r. In this case, that's 2 pi. Our radius is 13.5. And again, I'm going from inches to meters. So there's my inches to meters conversion ratio right there. 0.22 over 1. And I'll have my answer. Let's do it. 2 pi times 13.5 times 0.22 over 1. We get 18.66. Some of you might have noticed I did not divide 1 there. Anything divided by 1 is just itself. So I could just end it with 2 pi times that. That'd be our answer. Okay, 2 pi times 13.5 times 0.22, and that'll be our answer. Don't need to divide 1. Dividing 1 is, we're done with. I'll prove it to you. Divide 1. 18.66. Well, that's the same answer we got there. Okay, next one. How many times does a child's bike tire have to rotate for the bicycle to travel 1 kilometer? Okay, well, first off, we're going to realize that this is the child's bike. Right here is 8.29 meters. So 1 rotation is 8.29 meters. And we're trying to find how many rotations to 1 kilometer. Okay? So if one rotation is that, how many are in 1 kilometer? 1 kilometer, 1,000 meters. So how many times does this go into this? Well, what are we going to do? We're going to divide. Okay, so we'll say number of rotations is 1,000 over 8.29. So what's that? I don't know. Let's find out. 120.6. And what's the unit for rotations? I'm not sure what it wants us to look at. I think instead of RPM, it's just the rotations part. So I think it's just R. R for rotations. Okay. How many times does a woman's bicycle tire have to travel to go 1 kilometer? Well, remember that one rotation with her bike is, we found 18.66. Okay, so number of rotations is 1,000 again over 18.66. And we get 53.59. Our unit, I guess, rotations. All right, there it is. I believe that we have completed our assignment. Hopefully, most of it made sense. If not, then study your notes and try some more practice problems. I'm sure that you can find them online. And I guess I'll catch you all next time, guys. Goodbye.